We'll just go ahead and get started. So glad you all are here. And for those online, this is our April meeting for the North Texas chapter, and we're just going to go right into our speaker, and it is Mr. James LaDue. We just call him Jim. And so we all know Jim. Jim is the acting director of the National Windstorm Impact Reduction Program at the National Institute of Standards and Technology. Just to give a history for Jim, Jim graduated from SUNY Oswego, started working at NESDIS, working with evaluating severe thunderstorms with geostationary satellites, and then spent quite a few years, probably the last 15 or 20 years or so, with the National Weather Service with their training division, doing instructor-led courses, both in person and online, everything from tornadoes, squall lines, winter weather, and has now moved on to wind impact work. Jim chairs various committees, is a number of societies, and he's also an award winner. He's been on multiple awards: the Larry R. Johnson Award with NWA, DOC Gold Medal and Bronze Medal awards. So Jim, you're just missing the silver medal, and you have all that. And fun fact, I think he still wants to kayak a hurricane at some point. Luckily, we get a few of those every year. So anyway, Jim, glad to have you on board. The floor is yours.
Well, I guess I got an open topic, so I thought I would talk about various things, and of course, one of them is here's today's image of the sun. I think we're talking about space weather. Is that right?
Sure. Yeah, whatever you want.
All right. Yeah, we can dive into just about anything. I'm testing my new equipment, getting ready for the eclipse, so that when I pay my $1,500 room fee for a Waco, Texas hotel room, I'll be ready. So, in all seriousness, though, and let me know if I go out of line because we all know each other, and I tend to get out of hand. So, keep me in control. I am acting director right now of NIST NWIRP. NWIRP stands for National Windstorm Impact Reduction Program, and its whole goal is to mitigate adverse impacts from windstorms and related hazards. So it's not just wind, but storm surge and wildfire, and even rainwater intrusion into buildings, which now is a big issue when it rains heavily with a high wind event. So all sorts of interesting things. I was just down in Florida, in fact, doing a reconnaissance days after Hurricane Ian came ashore. And so now I got a really good dosing of what it's like to investigate storm surge damage as well as wind damage. But here I'm going to talk a little bit more about where we're heading with tornado intensity estimation. And I might generalize that to say more about wind speed estimation out of severe storms. So not just limited to tornadoes, but any kind of severe wind event, including hurricanes, derechos, and downslope winds, and who knows what else. So we'll leave it at that and move forward. This is a web page. This is actually, if you just type NIST and then NWIRP, National Windstorm Impact Reduction Program Office, you'll get this page here, which has all the latest highlights and everything else that goes along with it. It's kind of interesting working in the intersection between engineering and meteorological communities. And actually, in addition to that, dealing with forestry, tree ecology, all these questions. And not only that, but I'd have to say also soil science. And why is that? Because I'm just going to pull a picture out of left field here. This was taken not too long ago in east central Louisiana, where a tornado crossed a farmer's field and ripped up the ground to the depth of almost a foot deep and basically flung dirt clods over, just about everywhere. This is the same field. Right behind me was the farmer's house, which was destroyed, and he was recovered out of the house after some neighbors came over and pulled a wall off of him. and luckily he just suffered minor injuries, but he was really gracious. I mean, considering the trauma he encountered with that tornado, he allowed a few people from NSSL, Melissa Wagner and Eric Rasmussen and me to come down and investigate this damage. And this is something we rarely see. I think this is probably about tornado number 3 where we've heard of soil being ripped like this to a depth that it was. The last one was in 2011. That was April 27th, somewhere near Philadelphia, Mississippi. And so, yes, we're getting soil scientists involved. In fact, soil scientists from OU came down there to basically do a core sampling of this dirt to see, is there anything special about this dirt that would cause it to fold up like this and then crumple and then blow apart into big clods that you see right there. But it's kind of interesting. At least we can find out, hey, what's the soil stress of the wind upon, and figure out what is that limiting stress that would cause the soil to break apart into these chunks here. And so it might be getting some interesting answers. And in fact, maybe they also took samples elsewhere in the Perils domain, that Project Perils, which is studying quasi-linear convectively induced tornadoes. So anyway, that's what we got there. Let me go past the sun and just talk a little bit about this. I want to kind of walk you through a scenario here. So imagine a typical scenario where a tornado is coming through and it hits a small city. And as it travels along its path, it encounters a variety of different land uses, anywhere from dense urban to completely rural areas to wooded areas and everything in between. And you have a FEMA or other organizations want to know details of this path, not just to the extent that we do now, but at least in every method that we can apply to it to grab and extract wind speeds out of this. And maybe because there are plenty of uses for this, perhaps there's a building that was hit that should not have failed and it did, and they want an accurate wind speed assessment, or it could be any number of other things that they have to basically figure out. Perhaps it's the insurance industry that wants more than just, did it get hit by a tornado? Maybe they want some more details to help figure out whether it's the house or the wind. Now, I'm not saying that the insurance industry is going that way. This is just a hypothetical. So we're going to go ahead and use this. And this happens to be a tornado that we did encounter. And you might actually see a city name in there that you recognize, and you probably already know which tornado it is. But the standards committee, our standards committee is run across this because it just represents everything that we do. And as we walk through this tornado, we're going to see what I mean as we go through. So take a look at this. I've got several points here that we'll walk through as we talk about this path. And in fact, you can kind of see the origins of this path, part of it. You can see across the river here, and there are several areas where it's wooded. And then we have dense, mature residential areas. We have an interchange here with stores. And then we have a industrial district and then an airport. So as you can see, it is quite a variety here. But the amazing thing about this event here is that it came very close to an ASOS station. And there's a radar nearby, which basically is kind of like the capstone of just all the observing sciences we have. And actually a lot of high detailed aerial imagery was taken for this event too. So we'll start off and take a look at point 1 and trying to figure out, well, how can we gauge the tornado estimate, the intensity, at least in those regions right there. So let me go here forward here to the Ouachita Forest evaluation. So this is a forest land here in between that bend in the river. And we have several things that we can add to this here. And these are things that we're going through in the committee. And one of them is the nearby radar. So we can estimate, the radar is close enough that it can get details out of the tornado that normally we wouldn't be able to because the event is farther away. The other one, though, is a tree fall pattern technique, which is actually something that we don't see in operations right now. And that's what we hope to get into operations once the standard comes out. And we have several different techniques within this tree fall pattern. Tree fall percentage, this is published by Chris Godfrey and Chris Peterson in Weather Analysis and Forecasting several years ago. And we also have a couple sub types of methods here called pattern matching. So essentially what they do is they have the tornado vortex. You can observe the tree fall pattern. In this case here, I just created these tree fall vectors. So you can kind of see a sample of how these trees fell, and they did fall in preferred directions. There's actually a head and a tail, so to speak, or a tip of the crown and the root ball. And I can mark these, and then what we do is we actually take like an idealized tornado vortex, something that's a mathematical model. It's very simple. And we run that across a patch of hypothetical trees, model trees. And the model trees have a critical wind speed distribution attached to them. And so when the wind speed starts getting high enough, we kind of just roll the die. And first, the probabilities are pretty small because the wind speed's just not quite there yet. But then the wind speed ramps up. And as it ramps up, the probability of tree fall increases. And so we apply this technique and create a model tree fall pattern. And then after that, we can match the two. And once we play around with the parameters of the vortex model, we get a best fit, so to speak, and then we can use that vortex model to create a wind speed swath. And so I'm just going to show some examples of how that might play out there. And we have a multi-tree damage indicator that we're playing around with. This is something that was developed up in Canada at the Northern Tornadoes Project. Would you believe? I don't know how many of you have heard of the Northern Tornadoes Project, but if you haven't, it's really cool. That's something you can Google, and you see there's a whole project up there. Their aim is to document every tornado in Canada. Okay, and then on top of everything else here, we have a remote sensing assist with high resolution and also spaceborne imagery. So if I do this, and you can see the tree fall pattern here, and we've got all the tree fall vectors, and so there's the tornado vortex center line that runs right through, and I can take that, and we actually have software. A PhD student out of the University of Illinois has written this up so that I can take all those tree fall vectors that I made up, and then it comes up with a average tree fall vector. And I get to play with the parameters like the tornado speed, motion, the various inflow angles, how wide the tornado is, how fast do the winds fall away from the radius of max wind speed, and then what threshold tree fall do I want to have in terms of a threshold wind. So I can play with a lot of that, and I can come up with multiple options. These are some of the best matches that we have, and I can come up with a wind speed. Yeah, that's 150 miles per hour. Using something like this, getting that best fit. So this is an example. This would be kind of like this is an animation of how this idealized vortex runs through this forest, and you can see it knocks down the trees and comes up with its pattern. So that's what the model's doing, and I'm trying to take reality, match it, and adjust the model so it matches with the observed tree fall. So what does it look like here? Well, there's various tornadoes. There are common tree fall patterns with all of these here, in fact. For example, we have a herringbone pattern over here on the left. This was an EF3 out of Rochelle, Illinois. Relatively quick mover. The faster the tornado moves, of course, the more straight line the trees are. The slower it moves, the more curvilinear the tree fall happens to be. For example, in this right here in the middle, this is Joplin. You can see we have tree fall, lots of trees that move or have fallen in opposite to the direction of the tornado motion. So, and then if we get a really weak tornado, for example, that's relatively fast moving, we may not even have any kind of a herringbone convergence or a circular pattern or anything. It'd just be a patch of trees that just got mowed straight down along the path of the tornado. And so in a sense, the model is kind of objectifying these subjective patterns that we see, and then coming up with that wind field map. So this has been already applied to some relatively large tornadoes. NIST, that's the organization I work for, National Institute for Standards and Technology. They did a huge project after Joplin. This is an investigation. It was done under the authorization of the National Construction Safety Team. And they did basically an NTSB style investigation of building failure in Joplin. And part of that project was taking the tree fall pattern observed throughout the entire track and coming up with a detailed wind speed analysis through that, and then comparing that with the damage that they saw using forensics techniques and also the traditional EF scale. No radar nearby Joplin, unfortunately, so we couldn't deal with and take advantage of that approach. But we have, 3 other techniques here, at least, that they can use. So that's what we're drawing from. But in this case here, we got radar. And so let's apply it. So like with the tree fall pattern, the radar is assisting an idealized model. And so this is the model that one of the models that was used, and you can see this amazing detail and the wind speed contours and so forth. And so this is actually presented here by Don Burgess and co-authors back in the last severe storms. That was the conference, and it was held in Santa Fe back in last October. They did this, and we take a look at that area where we did that tree fall analysis, and we see this box, and boom, there it is. So this is something that we could use. I mean, here's another estimate method. It can come up with a wind swath. We get winds a little bit more modest than what the tree fall pattern has, maybe up to 134 miles per hour. So again, there are differences in this, and the variety of differences come about for various reasons. So, and it's probably hard. Sometimes we can know why those are coming about. Other times, a little bit more difficult. But we got them nonetheless. So we can take that. And the scope here is really just trying to figure out, just getting a general swath. It doesn't make any assumptions. We're not going to add any assumptions in there, because we know that the radar beam is at a specific altitude, and that altitude does not correspond to our convention that we want to all basically calibrate to, and that's the 10-meter wind that is 10 meters above the ground for a 3-second gust. And no, the radar, it can't do that, and we still don't know what that reduction factor is, taking the wind at wherever the beam is, dropping it down to the ground. So right now we're just not. The idea is just not to touch that. Just take the measurements that the radar has, and then provide enough information for the user to basically figure out what the user wants to do with it. So that's a big research topic down the road, basically. Can we do something else besides just taking whatever the radar shows? Can we find out enough information to come up with a meaningful reduction, depending on where you are relative to the tornado center, and also what kind of tornado it is, so forth. So that's a research topic, but it's been done. This has been done before, and the first time it was done was with the Spencer, South Dakota tornado way back in 1998. And this is Werman's. In fact, the Center for Analysis Prediction of Storms, now it's really called it's the University of Illinois Radar and Observation Facility. They're the ones that are responsible for this chapter, and and they've come along quite a ways, but this is kind of the thing, some of the things that we can produce with it. We can actually see an instantaneous picture of what the wind speed distribution is like around the tornado. You can tell here that the tornado is moving, and so therefore the strongest winds are on the right, or in this case, the south side. And so, or we can accumulate this over time to create the wind swath that you just saw earlier. So like with the tree fall pattern, the radar gives you both kind of a snapshot and also a total swath. So it gives you time, what was the wind speed at X time and so forth, and also a overall swath, something like that. So we did that for this technique, and we came up with an estimate. We have, and I just showed you this tree fall pattern. That was the highest value that I got, 150 miles per hour. There's also the tree fall percentage, and I didn't show you that, but that's basically taking the percentage of various plots of tree fall, and you do an assessment and then come up with a wind speed estimate. That was actually done by Todd Murphy and co-authors down at the University of Louisiana at Monroe. So you can see all these different variations, and we get a wind speed range of 120 to 150 miles per hour. And you look at this and go, well, okay, so some of them are in the EF2, some of them are in the EF3 range. And yeah, that's the nature of the beast right there, is that we do have uncertainty of wind speeds. Maybe when you're in the 120 to 150 miles an hour, you know, a range of 30 doesn't seem like much, but when you convert it to EF ratings, suddenly you're between a 2 and a 3, and it kind of inflates that. That's the way it is. So anyway, let's walk around. Maybe first let me just go ahead and go through this, and then we can open it up for kind of some interim questions or anything like that as we walk through. But let's step on to point number 2. And when we get to point 2, now we're talking about a residential area that's established. It's got a lot of trees, a lot of houses. Looks something like this. We got a neighborhood of 1 to 2 family houses, kind of old, they're not new. And we got lots of big trees, or at least we did. And so in this area here, since we have a lot of big trees, we can apply the tree fall pattern. We're still close to the radar. We're getting closer to the radar, as a matter of fact, so we can apply that. And then we also have the new and a legacy EF scale. So we're doing a comparison between the two, because the one thing I know that will be asked about when the standard comes out is, what's this going to do to our tornado climatology? We have a lot of old, legacy tornadoes that were already rated. Okay, some of them somewhat controversially. We have several tornadoes that people are going, why wasn't that rated this or that? And then now we have the new version of the EF scale. Hey, what if there's differences? Some of the tornadoes could change ratings when we go from the legacy to the new. And they're going to want to know. I'm sure that maybe the Weather Service might want to know, is that going to affect our overall climatology? So we're going to make this comparison, make others as well. But as we go through here, we're going to focus, and I'll just show you the comparison here. Right after this tornado this happened here, there was a team that went out and basically drove the entire path with Street View and drones, and got a lot of data. And so there are hundreds of damage indicators to compare from one to the other. This happens to be a house. So the traditional, all right, rated EF2, I think. Here's the picture of some of the Street View camera imagery, as well as as you saw, the overhead. Weather Service took a picture of it to the right. And, hey, you can see that all this data, in fact, if you point your phone camera at that QR code, you can actually pull this data up for yourself. So anyway, with this, we had 2 independent teams rate and evaluate these pictures to come up with ratings, and then we can compare them with the EF scale. And you can see there's a evaluator group number 1. They had a somewhat higher degree of damage, and so the wind speed was a little bit higher. That's the legacy wind speed. The new one is over here. We had another set of evaluators, and they go, oh, I don't know if it's that, maybe it's a little bit lower. And then they changed it down a little bit. And in this case here, they applied also, however, the same DOD for the new wind speed scale. Okay, and it came up with roughly the same wind speed. Well, why is that the case? Why is there a change in wind speeds even up here with the same estimated wind speed, same degree of damage, but then the wind speed changed from the old to the new? And it all because we're updating and changing the text in the degrees of damage in the new EF scale. So instead of here in the legacy, degree of damage 7, exterior walls collapsed. Now we have details such as this, where we have loss of roof structure greater than 75%, and or major wall structure damage greater than 50 to 75%. Interior walls remain standing. So a lot of information. But the wind speeds came up a little bit different. We rounded some of the wind speeds and adjusted some others and raised them. So it changes the wind speed. And in fact, in this case here, it could change it across an EF rating. So there may be details like this. Is it going to affect the climatology when you do this to thousands of degrees of damage and DIs and across hundreds of tornadoes? That's an open question. In many cases, we will find out, that's for sure. In this case, it would not affect the rating of the tornado. There were other structures that were damaged more severely, and so it's a solid EF3. But at this spot right here, well, we've got an 18-mile-an-hour difference among all these estimates here. Although, interestingly enough, the two different teams came up with the same degree of damage with the new, but had differences with the old, the legacy. Okay. So that being said, there's some minor differences, but we can see what the wind speeds were in that EF rating. If you look at all the damage indicators that we are proposing, at least at this time, okay, the ones in bold are the ones that are new or have major changes. They may have merged some of them. In other words, here with manufactured homes, we propose to merge the single and double wide into one category. But in houses, we propose a new one, the concrete block stucco residence, to separate off the wood frame. And the reason why is they're fundamentally different construction, very different. You go into Florida, and it's all going to be basically DI number 4. DI number 3, concrete block stucco residences. And most of the country is going to be pretty much wood frame. So we did this in general throughout, but you might be interested to see that we have one here, the passenger vehicle. That one's probably engendering the most controversy of all. It's difficult to get a handle on vehicles, different kinds of vehicles, different sizes, and different orientations with respect to a tornado, which is in itself a highly turbulent feature. So yeah, that's a tough one. Here's another one. You see these rooftop units? If you go on top of a big flat roof building and you see all those rooftop units, the air conditioning and so forth, well, they're all pretty much the same, whether you're in a low rise, mid rise, or high rise, or an institutional building or warehouse, or et cetera, et cetera. Why are we using those as degrees of damage among those huge varieties of damage indicators when basically they're all installed fairly similarly upon a roof? So that's why we're going to choose to make it its own. Down here, we have trees now, softwood and hardwood. By the way, that's not the approach that any arborist or tree ecologist would have taken. So now we have a proposed single tree DI, but within it, it's going to depend, its resistance, the tree's resistance to the wind will depend on species and tree size. Now, a young mature tree versus an old tree is a lot tougher against the wind. And likewise, some species are really tough, like live oak and bald cypress, as opposed to willows and silver maples. Another thing here that will really help the sparsely populated plain states, wind turbines and center pivot irrigation systems. Their wind turbines are popping up just about everywhere. And of course, almost everywhere in the drought-stricken plains are center pivot irrigators. So hopefully that will add a lot more information to those places. And, I think I mentioned all of those changes right here earlier, but this is it in a nutshell, at least what we have right now. So adding all this, okay, and these kinds of things, it's going to be quite a change. I mean, the fundamental method behind the EF scale will not change at all. Well, I should say there'll be some minor changes in that too. We are proposing slightly different things, and I'll show that in a little bit. For example, we have a lot more commentary in here. This is center pivot irrigator that has commentary in that. Some of the commentary can go on for more than a dozen pages. Trees is an example of that. There's a lot to unpack about trees. And so it's going to be an informative document. Heck, I mean, it's going to be useful to anybody, including landscapers and arborists all over the country. If a resident might want that commentary, might want to see which trees they might want to pick to plant around their house so that maybe the tree won't fall prematurely on there. So it's going to be a lot of widespread. It's going to be, the impacts of this is going to be huge, I think, once we get this out there. It'll be an awful lot of information. All right, so what else has changed? Yeah, we have a lot more detail in the degrees of damage, not just as presented here, but we have others as well that you'll see. And I think you saw a little bit of an example of that with the house and so forth. So essentially, there is going to be significant, but the foundational EF rating to wind speed relationship will not change. Not at this time. Even approaching that idea is going to take a big lift. We're not ready for that. We got enough stuff to deal with, at least right now. And the most important thing is to be able to get this through and get it out there. So we had all that and the considerations of the EF rating. But for that point number 2, we also have a tree fall analysis. And I came up with this right here. And this came up with 142 miles per hour. Best fit patterns given the radius of maximum wind estimates and how fast the tornado is moving, et cetera. That's what we approximated, at least in this area. We also have the radar data. In this case, it's contoured on top of the tree fall pattern area. Those are the blue vectors, and then the wind speed estimate from the radar, which is on the low side of all the estimates that we have between the EF rating that we got for that one house, which is right in that circle, and then also the tree fall pattern. So again, that's the nature of the beast. There will be differences. Needless to say, both the house and the max wind swath in radar are fairly well correlated, as well as the tree fall pattern. So we get estimates like this, anywhere from 122 to 132 with the legacy EF scale, more agreement with the new one, tree fall pattern 142 and radar 114. So the one thing that's of interest, I should bring this back. I did say well correlated spatially. the house is still on the north side of the max wind observed by radar. So there is somewhat of a geographical location of a few houses. And we see that on occasion, that the radar is seeing, and it could be because it's, again, sampling the vortex from a higher altitude. There could be a slope to that max wind as you go up in height. All right. So let's go here and let's step down the road a little bit. I do have a 0.3 right there. And this one is also an older, densely residential area, densely packed residential area. Maybe this is the most interesting point if we want to promote all these techniques, because they all showed rather similar trends as the vortex passed from west to east. In this case here, I've got the EF rating contours based on a combination of the ground cruise and then also adjusted by the aerial imagery in this area. And that's applying the remote sensing methods that we have, are basically support methods. And they show weakening. And it shows also in the radar data, that the radars in the dashed contours. But you also see, yeah, again, here, there's actually a southward displacement between the radar data and the observed data. So it's a little bit different, but also showing the same trends. Then we go up to the northeast, and now we're in a place, and I'm going to go to 0.6. And here we have the radar observations, the wind observations in dashed yellow. There's the EF ratings and the solid contours. And in this case here, we literally went from an area of what was basically industrial district, and the tornado went right out into an area that you pretty much could wind up being just as lacking in damage indicators as the high plains. So there's nothing there to damage, except for the fact that fortuitously there's an ASOS station right here, which had a peak gust of about 30.8 meters per second. And the radar is about 37.6 meters per second. Well, you know, 70 knots or something like that in the low 70s. So, and the radar is a little bit higher than what the peak gust was, but it's not like out of the ballpark higher or anything like that. You know, so 7 meters per second, 14 knots. So we can put all those together and get a better picture of it for this in situ data. If you think about it, well, I mean, how many times is a tornado going to hit an anemometer? Well, I don't know. It doesn't have to hit it directly. An anemometer could be in the tornado's wind field, and we can still get an idea at that point using these methods, you know, what that wind speed is like. And that wind field is pretty wide. It's wider than the historical record really tends to indicate. Because I think in the historical record, there was more emphasis on tornado cores, but the tornado has a huge wind field outside of that. And so this kind of technique will be useful. Like with everything else, though, it's a challenge. We do want to have wind speed estimates with a fairly similar exposure from let's say a wind speed estimate in the woods or a densely wooded residential area to an area that's wide open. And so a lot of engineers like to adjust that. In fact, the exposures guidance that's in the building loads chapters that the ASCE maintains as a standard, they all basically calibrate or adjust wind speed estimates to an open setting, basically a fairly open setting. It may not be as open as the ocean. It's mostly open to, maybe mostly similar to that of a field or something like that. So there are all sorts of techniques to change those. There are techniques to adjust the gusts recorded by anemometers to that 3-second criteria. And so we had that. We know these relationships. They're easy to determine for standard wind environments, but tornadoes, that's quite a bit different. At this point, I don't think there's going to be anything, although we are about to, and hopefully very soon, ballot the in situ chapter. And then we'll have a nice discussion about that. The remote sensing, we're talking also about looking at the large scale remote sensing. And here I have a picture of a product called the Normalized Difference Vegetation Index. Basically represents how degraded the vegetation looks after an event happens, in this case, a tornado. But also, this product picks up debris. So if there's a lot of building debris, it's going to show. This satellite image is a difference between the near and, let's say, a couple different near infrared channels or red channels. And it came up with areas where it does show degraded vegetation and or debris in these places. And then it shows a cessation of that debris off to the east, right along with the weakening of the tornado observed by radar and surface damage by the EF scale. So this tends to show something fairly similar. Weather service offices use this product from, in this case, the Sentinel European Sentinel satellite. These are polar orbiting satellites. And they'll use them to map the damage, especially in areas they could not access. So most of the time it works out pretty well. Other times there may be some differences. For example, if we have a lack of tree cover and or debris sources, we may not see an NDVI change because of that. And that might be the case, such as over this highway interchange, which is basically just a large area of lawn without houses or anything else. And so suddenly we don't have much of anything. But as this tornado passed east of the interchange, went over some stores, and then hit a new neighborhood right here. And that new neighborhood basically lost a lot of rooftops, a lot of buildings. There's now a lot of debris, which shows up in the NDVI. And it also happens to be in that area where there's some increase in damage enough to say, hey, this thing might have intensified some, which may be true. The radar, on the other hand, shows, yes, it was weak here. It strengthened over the interchange. And then that continued on to the east. So I think the evidence here, if you look at the grand scheme of things, the damage at the ground, the change in NDVI, and then also the radar, you can gain some confidence to say, yes, this tornado probably intensified over this area. Some of that intensification occurred in an area where you're not going to see a surface impact, and then some did. So it is useful, and that's why we have it. At that point, let me just hold off here. I shouldn't have done that, but I'll see if there's any questions or comments. I've been going on for enough time here as it is. So I managed to get out of that, so go back. Is there anything you want to cover, at least at this point, to go on? I don't have too much more to go at this point.
I don't know, is there anything?
I see Tim is there now.
Yes. Are there any questions online before we continue?
Yes, I have a question.
Oh, no. This is the stump the instructor question. I know this.
When do you expect this to be fall finalized?
Oh, that it will get out as, how should I approach this one? I made a push earlier, say 2 years. And the reason why I did that is I want to light a fire under certain people to do it. We're making another push now that we are going to see if I can finagle a couple of our contributors to get their chapter drafts out so that we can ballot that. And it's hard to get them, especially with academic people. And Tim, you and I both know how busy they wind up getting.
Yeah. Yeah, it's just that over the last couple of months, I haven't heard very much from our group, and it's like I just don't want it kind of going into an era of not doing much. I'd
No,
love
we
to see
can't.
this thing being pushed. I
Yes.
like the idea of the thwarts meeting. I like the idea of AMS annual meeting. So I think anything we can do to push this to get it at least to where we've got every section in it, that would be great.
That's, believe me, that is my goal too. And, so part of that, I think, there was that break. It's like, okay, what do we do now? There are a couple people I'm trying to light a fire under them to make them jump to get there. And we can talk about that offline about who those are. But the idea is to set up, some kind of a tempo to get there. And
I mean, we've made
find
great
as much innovation as
progress. We're like
possible.
80% of the way there
Yes.
in some of these sections. And it's like, well, I think the incentive to push it a little more to get it done, well, they'd be receptive to that. If you're 80% done, let's get it 100% done. Let's just that would be great.
I think you're absolutely right. We are too far to fail. We have so much stuff that we've made and created in here that it's almost there. But I'll tell you one thing. This is something that we have all these chapters. Each one represents a method. And the most important one is the updated and revised EF scale. And that sets the standard, basically the tempo right there. And we can't have anybody better in charge of that than who we've got now.
Right. I totally agree. And if some of these chapters aren't going to have people behind them to push it, well, then maybe they shouldn't be in this iteration of it. They could wait to the next iteration of it there, because this is an ongoing piece of work.
And this is something that I think is great about the standards program that ASCE hosts and keeps in charge, is that this is a process, an R2O process, research to operations, that is basically a vehicle. There are whole engineering teams, research teams, everybody that is involved, devoted to a standards process, such as the building loads. I mean, that's their R2O. This is another one. And so, some things may not make it because maybe the science isn't far enough. Maybe we just don't have the right team that can really push it through because there's too many questions or other reasons. There's always a next iteration and a cycle. Typically every several years.
This Monroe study is really interesting. Is there any such study being done for Little Rock?
Not at this point, but you bring up something because that also is close to a radar.
Yes.
And you have lots of surface damage indicators. But I don't think there's not the field teams to go through. I know you've just been there
right.
And so there's probably a lot of data, and I'm not, and not just Little Rock, but multiple other places too.
Sure. I don't know what the radar situation is for Rolling Fork, but at least in Little Rock, you got a really close radar there. It's not as close as in Monroe, but you have a lot of DIs. So you've got 2,500 houses alone, and you've got lots of apartments, strip malls, and we've got a little stronger tornado there. It's EF3.
That was a solid EF3. We also have, all right, whatever is showing up on the screen here is all preliminary. I'm putting that disclaimer out there. This is the editing version of the damage assessment toolkit. A fabulous, this is Little Rock here. Look at all those points. It's an amazingly rich trove of data that we have.
Yep.
Plus, we have high resolution imagery taken by Vexel Corporation. We have almost, it might be, I don't know if how many surface anemometers there are in this area. Probably mostly backyard anemometry if there is, but let me tell you how much there is of that, and that can be useful.
You've got
radar is
Burns,
pretty
you've got
close
Burns
too.
Park. You can run your tree model across Burns Park.
Literally,
There's
yes.
10,000 trees down there. That's yeah.
That's down in this area, which I
Yeah.
think this is it here.
Yeah. And then you have the Air Force, and I don't know if it's Air Force Base or whatever. They should have instruments up there.
So I think there's yeah,
Yes,
more
look
than
it up.
enough data here to
Yeah.
And by the way, I think to correct me, but well, it might not have been for this one. It might have been for Rolling Fork that the perils teams were nearby. That involved
were they?
multiple radars.
Oh.
I just talked to the PI, Tony Liza, and he said, yes, there's more than one radar with
Wow.
data collected. You got the aerial imagery there. I'm sure there was a lot of drone footage, and also this Vexel, this gray sky imagery. So I think that's another really good potential case study, which is this one. There it is. Right in this area. So another very hot tornado to take a look at. With a lot of
Where do you
data.
get these aerial images from?
So this is a an MOU. Well, it's the Geospatial Insurance Consortium. Basically, it's a group that uses Vexel as a prime contractee to take imagery for the purpose of first response. So that's FEMA, emergency managers, and NOAA.
Wow.
So the data are there, in this agreement for the Weather Service to use to map these tornadoes.
That's fantastic, because in a lot of these areas, it's hard to find a beginning and ending point because of the landscape.
Exactly. And
access.
this is so valuable, this material. And it's only meant for, and that's why I'm saying as a disclaimer, this is I'm not going to go into too much detail. I might be in violation of these certain usage agreements and so forth. I got to be careful, but this is extremely useful, and it is available. But of course, for anybody to use it, they would have to make an agreement or purchase the data from Vexel Corporation. And it's not the only high resolution imagery out there. You got Planet Incorporated. Planet Labs. There's the Worldview satellite imagery from NASA that's available, among others. There are probably others I haven't mentioned either. But you can see, the imagery they've taken, following hurricanes is quite amazing. There's been an awful lot of that, and they're not the only ones either. So, that in mind, yeah, the standards committee, and I'll tell you one thing right now, the standards committee is a lot like any committee where everybody is doing their work and contributing on a volunteer basis. And Tim is one of the people that have contributed the most so far, just the sheer tonnage of new information regarding damage indicators, which I have acknowledged and will provide some form of acknowledgement and recognition in the near future. So this really, we are here, the standards committee, to support the Weather Service and also the entire community of stakeholders that use the data. We want to have something that provides ways to estimate wind speed from direct measurements and also indirectly from the changes to the environment they leave behind. And so we're doing this, it's a multi-year thing. It is not simple, I'll tell you. If I had these people, let's say under my employ, and they could work 40-hour weeks, yeah, we would have had this done years ago. But basically it's a volunteer effort, and we have to fit that in where we can. The wind speed estimation scope, again, we're focusing on helping provide support to these, basically the signature standard. That's the building load standard in the American Society for Civil Engineers, called ASCE 7. And these wind speed estimates, again, from all these methods, may be different, but each has value in itself. But we are focused on small areas or individual points within windstorms, including tornadoes. And it's not just providing a wind speed for the entire tornado, but from the multiple estimates within a tornado, yes, we can use that to inform what we want to rate this. Here's another reason why this takes so long. In the spectrum of documents and the amount of scrutiny and peer review, a standard is number one in the amount of scrutiny it receives. Essentially, it is, and I think, Tim, you coined this, when it comes out, it's like law. All right. It's not a building code or anything like that, but it's a standard, like the USB standard that you get, to make sure all USB outlets are the same. It's really kind of the same idea. So that's the challenge. And it goes through this huge, to get through a standard, it goes through this. And we're in this rotating pattern right here. Okay. And we've been at it for some years. We'll continue at least for another couple of years. And eventually we'll get a draft for the whole thing, which then upon approval in ASCE goes out to the public to comment. And that might take almost a year. And once that happens, then there may be some changes that we have to do to go through, but we won't have to go through this iteration like we are now because we're creating something new. Once we get something new, we'd be 90% of the way there. So we got a lot of work. We have a lot of work to do. Oops. I think I bumped myself out again. In the process of doing that, and I'm just going to skip a little bit here. Yeah, this is what I want to show. I have a whole list of interesting webinars that we have. They're all on YouTube. And this is something that I can share with you all if you'd like. But lots of analysis, lots of science that goes behind the content that we have. A lot of things have been researched as a result of the standards activity that we had. And it's pushed the science even farther than it would have otherwise. And so I'll definitely share this so that you can understand some of the science that goes behind it. There are other related studies, by the way. Tim just did a paper, and this is actually not this session, it's a Severe Local Storms Conference paper. Todd Murphy and co-authors also studied the Monroe tornado, the content that I showed you, and have written an article in the National Weather Association, which is available here with that QR code. We also have Don Burgess and also Ali Merrily and co-authors compared the legacy with the revised EF scale. And they're about to come out. I think Tanya said she's at a 90% for the new journal article for that one. So that will be powerful. So the implications down the road, what's it going to do to the climatology? Well, I don't know. It's going to change it. Why? Because we have more of an opportunity to fill in the gaps. We don't know how strong tornadoes are in places where there's nothing to hit until you start putting stuff out there like wind turbines and power lines and things like that. And then suddenly now tornadoes have lots of opportunity to hit them. It would be nice to know what we're getting ourselves into. And according to several recent papers, there's a much bigger tornado threat out there than we are aware of with the climatology that we have. So that may mean that the return frequency that any building might be exposed to is higher than we are aware of. So we have that. There's, as a result of some of this activity that we have done, there's a new chapter in ASCE 7 called Tornado Loads for the first time ever. Some content in there to inform builders that there is something we can do about resisting tornadoes, contrary to a lot of popular opinion these days. And I've seen this too, especially in the manufactured housing business. You know, they think, oh, there's nothing we can do. Yes, there is something we can do. There's a lot. So I'll leave that there and then stop for now. Is there anything else you'd like to talk about, or have I burned my time and you're all ready to run out the door? I apologize ahead of time.
Oh, don't worry, Jim, that was great. Thank you so much for presenting with us. I know we're just past the top of the hour. I don't know if there's like one quick question if we want to address, or I know I have questions, but I can save that for another time. I know where to find you to harass you.
Oh, well, I guess if nobody else asks anything, you're certainly welcome to ask.
Yeah. Well, I'll ask one quick one then. Actually, it involves your simulations with trees, and I'm assuming this simulation there just have them fall where they originated. Does it handle things like if trees were lofted and moved a certain distance? Because I know what very few surveys I've done, I've seen that where trees end up where they were not growing.
Oh, that's a good question. I'll tell you one thing. There's actually the tree fall pattern technique does not account for continued dislocation of trees once they fall. And yeah, I know you've probably seen that as and I have as well, that yes, sometimes trees tend to have a tendency to blow around even farther than they have before. And that's the nature of the game. But the good thing about it is that the tree DI, we're going to change that to include trees dislocated horizontally. Okay, some distance. I think it has to include the root ball though. So it has to uproot first, trunk snappage. Yeah, I don't know about that, but it has to uproot and then physically dislocate somewhere else. And that will be a solid EF4 the way the proposal is right now. However, having said that, I'm telling you, the Jackson, Mississippi office is being very provocative. If they see tree damage that is severe enough, they are going to go EF4. And you technically are allowed to do that because the top of the scale for the highest degree of damage in a tree is 2 miles per hour into the EF4 range. So here's an example. I think they rated some of this stuff in EF4, and I'm, you can disagree or agree as you see fit, but I think they were in this area. This is northeast of Rolling Forks, Mississippi, and there are trees. They mentioned, what is it? Yeah, trees, extreme damage. Majority debarking, most extreme damage I've seen. It's well, I don't know if I see that here in this case, but they were there and I wasn't. I don't know if they have another picture here or not. No, maybe not there. But they have other tree pictures. Here's snapped or tossed. They have trees that are snapped and tossed. I think that's one thing they're doing. So they're basically pushing the cart, so to speak. But of all the offices in the country, I would expect them to have the most experience dealing with this, considering the tornado exposure they have.
Cool, thank you for that.
So, Jim, I have a question. Is there any applicability to any of the derecho events, like any of your analysis or any of the work that you do could be applied in those situations, or is this strictly just for tornadoes?
So, yeah, some of the chapters are devoted to tornadoes. The tree fall pattern, for that example,
Right.
needs a vortex model. Radar, yeah, you can use radar with constraints in mind, right? Because you have to well sample the winds in there. So it might be tough to really come up with something if your radar is in the Quad Cities and your damage is in Cedar Rapids or something like that, 60 miles away. But yeah, certainly radars can be applied to any phenomenon. Forensics engineering and analysis, any phenomenon. EF scale, I know intent is meant for tornadoes. It's been applied to other phenomenon. And so it's been done. There's published precedent, so to speak. So I won't comment. I don't think we're going to arrest anybody who uses the revised one either for another. But there's going to be some disclaimers for that. Essentially the vertical profile of winds in a tornado are different. Therefore, the loading is different in a tornado than with typically other phenomena, except maybe if you're right next to a microburst or something like that. So anemometry, yeah, it's a lot easier actually. So that's been done, like with the Iowa derecho.
Cool, thank you. So I guess we'll start wrapping up our meeting here. So Jim, thank you so much for your time and all the effort that you've put into this. We do have
welcome.
we do have an Amazon gift card for you that I can either find a way to mail it to you, or if I can see you next time I'm in town, we'll do that. Oh, nice. Oh, it's so bright.
If you buy me lunch, I think we'll even. How about that? I'm just kidding.
We'll discuss, and this is this is what we do. So get fun, cool things. Other than that, just to cover real quick chapter business, the next meeting is going to be May 9th. Same time, same place. Our speaker is going to be Brenda Phillips from UMass. She's the director, and she's helped set up the CASA radar network here over DFW. And according to our communications, she'll actually be here that day. So wow. This will be fun. Of note, next meeting is the last meeting of the season, so officer elections will occur. And I don't know, is there any other chapter of business? Right, Stanley? Weird meeting. Dave? Not here. All right. With that, y'all have a great evening, and we'll talk to y'all next month. Have a good night. Good night.
Thanks, everyone.
All right.